Okay, thank you very much. I was told to start slowly while the air conditioning kicks in, so maybe I'll do that. So I'm going to be talking about a deceptively simple question, which is I want to consider a Q-form field strength F, which is closed. So that implies that locally there's some Q minus 1 form potential. And normally, as a free field equation, I demand that this also be co-closed. But I'm interested in a self-duality condition, so imposing that this is equal to its Hodge dual. So for that to make sense, I need the dimension to be twice the degree of the form, and I'm in Lorentzian signature, and I want my forms to be real, so I need this to be equal to 4n plus 2. And then this condition, together with the closure, then implies co-closure. So this implies the usual field equation, but is stronger. And for the usual field equation, one can use the usual Maxwell-type action integral of f wedge star f. But to get this action, this field equation, there's a question about what action, is there an action to give this field equation? So this is an old question which has been addressed for many times. So the work I'm talking about was in a paper which was put on the archive last week, and I tried to look at look at the attempts to construct actions for this, and I found something like 50 references, and that says two things about the problem. One is a lot of people thought it was worth investing time in, and that each of the 50 people were not satisfied with the answers of each of the previous ones. So there's a big problem to try and find an action a covariant action which gives this field equation, or even a non-covariant one. And a lot of the actions have got various issues with them. So why do we need an action rather than just a field equation? And the answer is, for the classical theory, all one needs is the field equation. But for the quantum theory, one would like an action. In particular, one's interested in the interactions of the field with other fields. So that, for example, hidden in this star, there's the interaction of the field with the metric. Given a metric, one can construct a Hodge star, and given a different metric, one gets a different Hodge star. And this implies the field equations for co-closure with respect to a given metric. A lot of the kinds of actions people try are to add some kind of Lagrange multiplier, add some form wedge f minus star f, for example. So then lambda would be a Q form whose f would be given by dA in this action, and varying lambda would then give the right field equation. But the catch is that then this lambda will become a propagating field, and moreover, it would be coupling to the metric implicitly through the existence of this metric hidden in the Hodge star. And this doesn't give a satisfactory action. And another approach would be to take something like and so we're going to look at different variations in that. And that's sort of, in essence, one of the problems with constructing such things, that you typically get extra fields, and there doesn't seem to be any way of getting rid of that. So as I said, it's a deceptively simple question, but there doesn't seem to be, but interestingly, trying to answer it seems to require introducing extra structure, and that's going to be and that's going to lead to some interesting geometry, which is the key to my talk. So a few years ago, a remarkable solution action was proposed by Sen, who was motivated by looking at string field theory. And in string field theory, there's an answer to very similar questions. And in particular, he constructed a string field theory action for the 2B string, and constructed an action which gives rise to these kinds of questions. So before going on that, let me just say a few more things about the requirements one would want for such an action. One is that one would want it to be quantizable. One would want it to not give extra degrees of freedom which interacted with the physical fields, not to give extra degrees of freedom which contributed to the theory. And one would be interested in looking at something which would be extendable to an interacting theory. So, for example, the two kinds of interactions one's interested in is one where one has f equals dA plus omega, where omega is some source term or Chern-Simons term. So, for example, in 6 dimensions, where f is a 3 form, one's often interested in adding a coupling to Yang-Mills theory through a Chern-Simons 3 form here. And so then one would get this equals d omega, which would be a covariant quantity. And the other kind of generalization one might be after is a higher derivative one, where one introduces something which, where if one defines f plus or minus is equals f plus or minus star f with a half, one could be interested in, instead of the constraint that f minus equals 0, which is the self-duality condition, we could more generally have that this is equal to some function of f plus. That also is a consistent story which reduces the number of degrees of freedom by half, and typically it would give rise to sort of Born-Infeld type field equations involving higher derivatives. And it's consistent because one can show that it correctly gives rise to those kinds of stories. So one wants a story which could be generalized to include Chern-Simons or sources and to higher derivative interactions, because those are some of the things one would want for string theory. Yes?
Is it possible to do that Lorentz covariantly?
That's the point of this talk. So the field equations I've written down are Lorentz covariant, and the question is there a Lorentz covariant action? And Sen wrote down a rather interesting action, which does go some way to solving this, but it also has some shortcomings. So let me describe a little bit of what he said. So as well as having yes, I should also say that the cases when dimension is 2, 6, and 10 are ones where these kinds of fields enter into string theory, and these are very important. Understanding these chiral form fields in those dimensions is particularly important for a lot of applications to string theory and M theory. So he had a field satisfying this, And then there was as well as df equals 0. And then there was another Q form, G, which was also closed, but instead of satisfying this satisfied a Hodge duality with respect to a Minkowski metric. And for here, eta is a diagonal, is a flat diagonal metric like this. So he involves a field G which couples is self-dual with respect to this eta, whereas the dynamical metric G, on a manifold equipped with a metric, whereas this couples to the metric G. And his argument is that here F is the required self-dual field, and G is an extra field which is auxiliary. As it seems inevitable, there's more propagating fields. But here, this field, F equals dA locally and G equals dC for some Q minus 1 form potentials. But these fields don't couple to the space-time metric or to any of the other fields. And one can take generalize to F equals dA plus omega and introduce coupling to other fields. So one has a physical sector consisting of the field A or F, the metric, and the other fields. So in the context, we could be thinking about type 2b supergravity, where in 10 dimensions, where this is a 4-form field, this is the metric, and these are the other fields in the supergravity theory, and an auxiliary sector consisting of G or C, and possibly we could include eta here, and these don't interact with these, so C just doesn't interact with any of the physical fields. And so his argument is it's an auxiliary sector which can be ignored, and he argues that this gives a good description, a good action for the self-dual field. Moreover, his action, which I'll talk about in more detail explicitly in a moment, is quadratic, so for the free theory, so it's easily quantizable, and one can check that it's gives precisely the answer, the kind of answers one would have wanted. And as I mentioned, it generalizes to the interacting theory. Now, the problem with this is the existence of this object eta. Now, if eta is another metric on the space-time, then it's restricting ourselves to spaces which admit a Minkowski metric, which is very restrictive. Essentially, it's locally flat space. And so G is just a perturbation, is on that restricted manifold, and G is restricted to be a perturbation around that, essentially. And what one would like would be an action which you could use on any space-time manifold, not just not just flat space. In Sen's paper, it's not entirely clear what the status of eta is, because he works in a fixed frame where he's introduced an orthonormal frame and then fixes gauges, so it's not quite clear whether the indices on this are flat or curved. But if this is a tangent space metric, then in dealing with this object here, one needs to couple it to a fieldline and use, and so there's in that case, there's an implicit coupling of this to a space-time metric if one tries to write down the action in a global form. So it seems that this is very restrictive, and another problem with the presence of eta is whether the kind of action he writes down is really coordinate independent. He writes it down with a particular form for eta, and it's not clear what and in particular, it's not clear what the geometric status of his action is. And finally, he has some very strange symmetries which look like diffeomorphisms for the fields in the physical sector, but leave these fields invariant, so they're not proper diffeomorphisms on the manifold. Any field will transform under a change of coordinates. So there's a question about what his strange symmetries are and how that works. So what I'm going to talk about today is a generalization of what Sen did, where instead of a flat metric eta, I introduce a second metric, which I'll call G bar. So I'm looking at a manifold equipped with two metrics, and this is self-dual with respect to the metric G, and this is self-dual with respect to the metric G bar, and then there's no eta which appears anywhere, and now eta is replaced by G bar, and we have a manifold equipped with two metrics, and we get an action describing two sets of fields, one consisting of just of the desired field, the metric G, which will be the dynamical metric, plus all the other physical fields of the theory, for example, of a supergravity or string theory. And the auxiliary sector consists of just C and this G bar. And these fields don't couple to each other, but not to any of these fields. And so in this way, we get an action for the desired physical fields, plus a kind of hidden sector describing these other fields, but in a way which, because we're not restricting on the form of G bar, this can be something which can be used on any manifold. So at the expense of introducing this extra metric, going to this kind of bimetric geometry, we're able to, I'm able to give a straightforward generalization of Sen's action, which works for any manifold, and in particular, we'll be able to look at, say, type 2b supergravity, an action for type 2b supergravity, which includes a chiral form field on any 10-dimensional space-time. And in doing this, it leads to some interesting questions about the geometry. We're very used to Riemannian geometry, the theory of manifolds equipped with one metric. But there's some interesting stories which arise when you've got a manifold with the extra structure of having two metrics. And this kind of bimetric geometry will be something which I aim to explore. So one of the things is that if we think about these as fields, we'd expect a gauge symmetry which, if we think about these as gauge fields, we'd expect a gauge symmetry when this transformed as under linearized transformations like this, and we'd expect, for a free theory, one might expect independent gauge transformations in this way, if we think of these as two spin 2 gauge fields. However, we also expect diffeomorphism symmetry, and diffeomorphism symmetry would arise as the diagonal subgroup of those. And what we'll see is that there are indeed two such symmetries arising in this theory, and in this action which I'll write down, and that has interesting implications. And one other kind of application one has for a similar kind of geometry is so-called massive gravity or multigravity. And this is the idea that one can consider actions with two metrics, one which would have the integral of star g r of g, the Einstein action for the metric g, plus the one for the action for the g bar, and add on certain kinds of interactions for g and g bar. And this, there's lots of reasons why one might expect this would lead to trouble, but quite recently, or well, not that recently, there's been remarkable work by Derome, Gadadzatsi, and Tolley, which showed that in the absence of this, one can choose interactions here such that then this interaction with a background metric gives rise to a consistent ghost-free theory of massive gravity. And this was then generalized to a theory where you add a kinetic term for g bar, and there are consistent interactions for two gravitons interacting with each other via a non-trivial interaction which leads to a ghost-free theory. And this generalizes to any number of metrics. And the same kind of structures that we'll talk about today also are very relevant to this story. In particular, these interactions, as originally formulated, depend on taking the inverse metric g bar times g to make a 1-1 tensor and defining a matrix square root of that. And this interaction could be written in terms of a matrix square root. And some of the issues I want to discuss are related to understanding geometrically what it means to take such a square root.
For example, if you actually use the Kaplan formulation, then you use the fear binds and the spin connection, that curve is easily run down as these cosmological curves type of interactions, where only the fear binds interact algebraically.
Yeah. Yeah.
So, without introducing square roots,
Yeah.
you use the fear binds.
Yeah.
And this term is a purely algebraic curve, like a
Yeah.
cosmological curve.
Yeah, exactly. So there's other ways of formulating it. As you rightly say, one can introduce frames for this one and frames for this one. And there's similar problems to the ones I'll describe, which arise in that formulation, namely that there's two local Lorentz symmetries, one for each frame, and the interactions which they write down it would break that symmetry to a diagonal subgroup. And in general, there are consequences to that because one can't always, because for a general two frame bundles, one can't always do that. So so locally that's fine, but there are global issues with that formulation which are equivalent to the global issues which arise with this. Yeah, it's the same problem. So I presented it one way, and as he rightly pointed out, there's a related way of thinking about it in terms of frames. And as usual, you can move things around, but there's equivalent amounts of trouble when one does that. Okay, so let's be a bit more precise and look at the form of Sen's action. So let me start off with Minkowski space. So I'll start off with RD equipped with a metric eta. And the action he writes down involves a Q form Q, which satisfies the self-dual with respect to this metric eta, and a Q minus 1 form P. And the action he writes down is a half dp wedge star dp. So far all the stars are with respect to eta. minus 2q wedge dp. And then analyzing the field equations, it leads to a definition of two objects, which are composites, which are made out of these q's and p's. There's a g, which is defined to be a half dp plus star dp plus q, which satisfies that g equals star g by definition, and as a result of the field equations from this action is closed, and f equals q, where f equals star f because q is self-dual, and as a result of the field equations, this is satisfied.
Sorry, but here all of a sudden we allow ourselves to have a field q which is by definition self-dual.
Yes, so that's the key point. So, but it's not, so the problem is if you have it being both exact or closed and self-dual. So having a field which is self-dual on its own, but which doesn't satisfy any differential constraints is fine. But the problem is if you were to try and define it to be, so the framework is that if we go back to this story, I talked about there are two equations to satisfy. One is df equals 0, and the other is f equals self-dual. So this here I was solving f equals dA by having solving this by having f equals dA and having a Lagrange multiplier imposing the other constraint. Here I'm doing something a little different, sort of the converse. I'm having f being self-dual, but having an extra field which imposes that f is closed. So varying this action with respect to p tells you that q is closed. And so this is Sen's solution.
I'm a bit confused because Q was self-dual with respect to eta.
Yeah. So here this is a warm-up exercise, and I'm going to put in a metric, and I'm going to change this to a curved manifold in a moment. So this is the warm-up exercise just to understand the structure. So the first thing I'll do is I'll talk about this kind of generalization, which is I can add an extra term minus f of q. And if I do that, if I define delta f, if the variation of the integral of f is 2 delta q wedge m of q, this defines what m, so m is basically the derivative of f defined in this way, then it follows that m is anti-self-dual with respect to eta, and then the field equations are that if we take f equals this, then f no longer is self-dual, but it satisfies this equation, no more that f minus equals fm of f plus. Adding this term makes it a little bit less trivial, and one gets this nonlinear generalization. So now, Sen's generalization of this, so this is the basic idea. So now I want to replace RD by some manifold, M, which is equipped both with eta and G, and I'll have that this is self-dual with respect to the background eta. So here there would be a problem, a potential, it's very convenient to choose this to be self-dual with respect to the background metric rather than the dynamical metric, and that's what's done here. And then this, there's an eta here and an eta here, and F plus and minus are defined with respect to the eta there. And then everything goes through. So this is self-dual with respect to eta. And then the remarkable thing is that with this, one can choose, so this is the remarkable part of Sen's construction, choose M in such a way that this equation implies that F equals star G F. So it's and where M is in fact linear in Q. So what he did was he showed that, or he argued that you could construct such an M, or rather he constructed such an M, but in a way which was very non-transparent. In particular, he constructed it as a power series, essentially in the perturbation between of G minus eta. And there's a lot of issues about the geometrical meaning of that and whether it could be done globally and whether it could be understood non-perturbatively in closed form. And that's one of the things I want to try and explain today. But his solution involves this non-trivial choice of M, of the matrix M, which is different from the manifold, which is meant to be a curved M, a curly M, and in such a way that this action gives rise to precisely what's needed. And in particular, G just couples to the background eta, and whereas F is self-dual with respect to the metric G and couples to that metric. And also this formalism allows the addition of sources or Chern-Simons terms. And so this was Sen's remarkable solution to the problem. And one of the key points is that his argument that you can find an M which does this. So this is the key structure. One further point is that when you do a Hamiltonian analysis, you see that the physical field F has positive energy, but the auxiliary one, G, has negative energy, so it's important that it decouples from the physical sector, otherwise it would be a bad thing. So this is the story in Sen, and so my story here is to replace eta with another metric G bar, and then the construction is very similar. I'll call the Hodge dual with respect to G bar star bar. So this becomes star bar here, and this becomes star bar, and that becomes star bar, and then everything goes through in that way. So the issue is understanding, then is one of understanding how M is constructed and what is the meaning of that. So are there any questions about the construction before we go into looking in more detail? Okay, good.
Sorry, maybe just the relation between F and M. What's the more fundamental of the F and M?
So here, because it's linear, one has that curly F equals Q wedge M of Q in this case. More general things are possible which would give Born-Infeld story, but for the purpose of this talk, I'll just take the case where this is quadratic. And if one introduced a basis for the self-dual forms, let's call it with label A, then this is just QA, QB times some matrix MAB. So the integral of this is the integral of this, which now I need to put in a volume form. And the point is that the only place where the metric G appears in this action is through M. And so there's all the other terms in this action just depend on G bar. And it's only through this term, which I've written in this way, that the metric actually enters. And
so M is a three-dimensional form constructed from Q.
yeah, so it's a matrix constructed from the two metrics, G and G bar, if you like. And I'm going to say explicitly how you do that in a moment. Well, fairly explicitly. But one can write down, one can make some choices and one can define exactly what this M is. And here, in a given basis, it's some matrix which one can write down, given the data which is in the two metrics.
The paper what we stand, this is a kind of obscure part. I mean, in some sense, it says, okay, I have some equational motion.
Yeah.
And this equational motion coming from effectively supergravity.
Yeah.
And I want to construct math in such a way, the equational motion that you coincide with that.
Yeah.
So, regarding to Dario, question is, somehow seems to be more fundamental than the little m. Okay? The little m gives you the equational motion to refer to, and therefore you construct f in such a way that you can use exactly those equational motion on those constraints.
Yeah. So, yeah, good. So one of the points of this work was trying to understand what's really going on in the geometry of Sen's obscure construction. And so given that for the quadratic theory I'll be talking about, M is linear, and so this term is just quadratic in Q, whether we talk about F or this matrix MAB or this linear operator are all equivalent. It's just different ways of packaging the same information. For the nonlinear story, for the Born-Infeld, the story is a bit more complicated, but we're not going to talk about that today. Yeah, so the aim is to understand how to construct that. So, So given two metrics, and G bar alpha beta, it's useful to have a way of converting from the story from one to another. If this was a flat metric, or the tangent space metric, one would introduce field binds to convert the story from one to another. And what I want to do is introduce an object which I'll call F, which F I'll call an interpolating structure, because it interpolates between these two different objects. So one can always construct such a thing locally. So this may be either local or global. Local means we construct an F in each patch so that the F in each coordinate patch, F is a tensor on that coordinate patch. And the global case when these patch together to form a global tensor. And it's always possible locally, because if we take local frames E for G and E bar for G bar, where these are the standard field binds for these, if one defines E mu A nu, then then it's easy to see that this satisfies this equation. And there's some redundancy here that if F satisfies this equation, then replacing F to L, F, L bar in matrix notation, where L is orthogonal with respect to the metric G, and L bar is orthogonal with respect to the metric G bar, then this will again give another solution here. So these are defined up to such local Lorentz transform OG and OG bar transformations in this sense. But the key thing is that given such an object, it enables us to convert between the two different kinds of Hodge duals. Using F, there's a map, I call it phi, from R forms to R forms, which takes a form omega mu 1 up to mu R to F mu 1 alpha 1 omega alpha 1 alpha R F mu R alpha R. So F acts as an automorphism of the, locally at least, of the space of R forms. And the key thing is it's easy to check that phi, taking the Hodge dual with respect to G bar and then acting with phi is the same as acting with phi and then taking the Hodge star. So in other words, it interchanges it maps between the two kinds of Hodge dual. And that's the key that one needs, because the key thing was to construct an M in such a way that we were able to map from a Q, which was self-dual with respect to G bar, to an F, which was self-dual with respect to M, with respect to G. So this gives us our construction of M, the matrix M, or the linear operator M, now in a very straightforward way. So we're given Q, which satisfies this, and we want to construct F, which is Q plus MQ, such that F equals star F. So given F equals star F, we can work backwards. That implies that because F equals star F, that implies that that phi minus 1 acting on F is some object U, where U equals star bar of U. So the point is that something which is self-dual with respect to star is mapped to something which is self-dual with respect to star bar, and vice versa using this map. So in particular, taking f and acting with phi minus 1, given that f is self-dual with respect to star, it will give something which is self-dual with respect to star bar. And so f is phi of u, but it's also equal to, so if I introduce projectors which are a half 1 plus or minus star bar, then one has that from here that f pi bar plus f equals q, because the variation of f is q wedge mq, because q is self-dual in the dimensions I'm working in, that means that m must be an anti-self-dual form, so with respect to g bar. So if I look at this equation, if I project the self-dual part with respect to g bar plus, g bar is q, and the anti-self-dual is this, part is this. But this is also equal to pi bar plus of phi of u, and this is equal to pi bar minus of phi of u. But now the idea is that we can eliminate u from these equations and to get m as a function in terms of q. So that works by saying that this is equal to nu, where n equals pi bar plus phi pi bar plus. Because u is self-dual with respect to this, I can put in this pi bar plus here, and this is equal to ku, where k equals pi bar minus phi pi bar plus. And then if I can find a generalized inverse for n, and let's call it n tilde, such that n tilde n equals pi bar plus, then that implies that then we can invert this to say that u equals n tilde q, and then we can put this in here, and we see that m of q equals k n tilde acting on q. And this gives an explicit, gives a construction of what m is. One can expand this out perturbatively and check that it agrees with Sen's construction. But this, but moreover, one can calculate locally and find that, and check explicitly that n is always invertible, and one can calculate these explicitly in terms of the eigenvalues of g and g bar. And that's, I do explicitly in the paper. But in this way, one constructs, for any g and g bar, one could construct an m in such a way that the field equation tells us that f equals star f with respect to g as required. And so that's the key to the construction. and that completes how one constructs the action. And in the little time remaining, I want to make some comments on the symmetries as promised. So an alternative action one could consider for the free system is if one were to consider integral of f wedge star g f minus integral of g wedge star, that's with respect to g, in this respect to g bar, of g, where g equals dc, f equals dA, and we supplement the field equations with the constraints g equals star bar g and f equals star f. So this is not really an action which does what one wants. It gives nice field equations which describe the coupling to the gravity, but the problem is that it doesn't give the right ones, and one needs to add these constraints. But nonetheless, this is something which is often considered. But if we were to consider this kind of action, then it's clear that it's invariant under diffeomorphisms of the manifold M, G, and G bar. But also, it's clear that one could consider something like some sort of chiral form of diffeomorphisms where one acted with diffeomorphisms on F and G and left this piece unchanged, or with diffeomorphisms on capital G and little g bar and left this part unchanged. And so one would see that one would, given this free decoupled form of the action, it actually has twice as many symmetries as one would normally expect. But of course, any interactions would usually break this to a diagonal subgroup. But nonetheless, it turns out that so there's two sorts of symmetry. So let me write down the two kinds of symmetries I mentioned. One is where you have delta G equals Lie zeta of G, delta F equals Lie zeta of F, and delta G bar equals delta G equals 0. That's clearly a symmetry of this, and it's not acting on this at all, so it's a symmetry of that. And there's a second symmetry where you have delta G bar equals Lie of another parameter chi of G bar, delta G equals Lie chi of G, and delta G and equals delta F equals 0. So the real diffeomorphisms are a diagonal subgroup, but these are clearly invariant under those separately. So the remarkable thing is that my version of Sen's action, my generalization of Sen's action, has precisely these kinds of symmetries, transformations which one which acts on G and F and the other physical fields, but not on little g bar and capital G, and another one which just acts on the auxiliary sector. And the transformations are almost these. They differ from these by off-shell trivial symmetries. This leads to this leads to some interesting questions about the global structure. The usual way of talking about things would be if to have to talk about the diagonal subgroup of these. And then it's remarkable that the action that I wrote down is invariant under, is globally well defined and invariant under these diffeomorphisms. So a key part of the construction was a choice of a local interpolating structure, little f. And I show in the paper that the construction I've given of capital M is independent of the choice of little f. I showed the ambiguities in little f are these local Lorentz transformations that I mentioned, and one can show that this construction of capital M is invariant under those. And in particular, that means that if you had a local interpolating structure, in the overlaps, the way they would be glued together would be by such transformations, such local Lorentz transformations. And because M is independent of those, that leads to the theorem that the capital M I've constructed is globally well defined, and the action is covariant and independent of the choice of coordinates. The details of the proof are in the paper, but I wanted to finish by talking about one of the consequences of this story. So here we have gauge transformations, which is more general than the diffeomorphisms. We've got two kinds of gauge transformations. And when you've got gauge transformations, when one's constructing a global theory from local data, where one has two patches, U and U primed, then in patching them together, you can use diffeomorphisms, but you can also use gauge transformations. So a standard case would be if the coordinates here were x primed and here x, then in the overlap one would have x primed equals some smooth function. I've used f already, let's call it k of x. Then if one had, for example, a gauge connection, so this would be x plus a parameter psi, a vector field plus this. Then if you had a gauge connection, the transition functions would involve a diffeomorphism plus, but you could also have a gauge transformation d lambda, and here I've just given the local form, the infinitesimal form of the transformation, so one would need to integrate up to give the global form. But for a tensor field, we would just have diffeomorphisms appearing here, but for a gauge field, we could also include gauge transformations. Here, this is constructing something which is not a tensor, but is a connection on a bundle in the standard for the Yang-Mills bundle in the standard way. But here we've got the possibility of, here we've got these objects G. If they were tensors, they would be glued, the transition functions would be G primed equals Li psi G, or the global form one gets by exponentiating that, so that you'd have the induced map given by the diffeomorphism, the push-forward map given by the diffeomorphism in the standard way. But here, there's also these gauge transformations which could occur, so that one would have G bar primed equals Li psi of G bar. This is meant to be a psi. But just like here, we could add gauge transformations. Here we've got these two gauge transformations, so there's a possibility of adding Li zeta of G here, and Li chi of G bar here. There's a slight redundancy in the way I've written it out, because the diffeomorphisms are the diagonal subgroup of here. But this is kind of remarkable. So If we take G, which is meant to be the physical metric, to be a tensor, we would choose zeta, this parameter zeta equals 0. But for G bar, which is some auxiliary field, which we've learned is a gauge field transforming under these transformations in this way, we could also add a transformation under the chi transformations. And here there's a remarkable possibility of, if we take, because these are the same form, if we take chi equals minus psi, so psi is the thing which tells you about the changes of coordinates you use in gluing together the charts, and chi is the parameter of this gauge symmetry for which G bar is the gauge field. If we take these two, then this remarkably gives G bar primed equals G bar. In other words, the components of this object would be unchanged under the transition functions, which is a rather strange generalization. So for the purposes of this talk, I've been talking about G and G bar as tensor fields, in which I would not allow this possibility, and then these would the standard kinds of transition functions. But this theory actually allows a more general kind of story where we allow transition functions for this auxiliary metric to be to include these gauge transformations. So it's not a tensor field, but it's a gauge field in the same way as A is. So it's some generalization of a gauge connection to a symmetric tensor. And in this case, we'd enabled us to use something whose components were the same in every patch, because the gauge transformation cancelled out the diffeomorphism. Of course, one could also construct more general configurations where this was not true, and this would allow more general configurations. Sorry? So in particular, this would allow you to take G bar equals eta, even though that doesn't make sense as a tensor, it would make sense as a gauge field in this way. So that was the punchline I was coming to. So in this way, understand this. What I've shown is I've shown how to understand the geometry behind this construction. And if you were to allow this kind of more bizarre kind of object in your theory, where it was a gauge field rather than a tensor field, then you could use Sen's action in that sense. But in a more conventional approach, one would take G bar to both of these to be tensors, in which case you would need to use the action that I described. But in particular, the action locally, there's no difference. They're related, but globally, it makes a difference as to how these things work. And in actual applications where one wants to actually do quantum calculations, then if one uses G bar as a metric, as a tensor, then one can use one's standard understanding of geometry, whereas in this more complex, in this more unusual way, it's not quite so clear what is going on. In particular, in doing quantum calculation, one would be interested in understanding how the result depended on the moduli of the metric, and using a reference in this way would be understanding the calculation in the path integral way. One could make contact with standard calculations much better if G bar was a metric. So one thing I didn't mention was that this interpolating structure, which I wrote down, given by G equals F G bar F transpose. This F gives a way of defining a natural square root of G bar inverse G in a sense, and is is related to the kind of ways which are used in the massive gravity which I mentioned. So I think it's rather interesting that this kind of structure with F seems to be a key to understanding this construction, in particular how to interchange between duality with respect to one metric and another, and also it seems to be a very natural thing to do in the context of biometric geometry, the case where you have a manifold equipped with two metrics. So, so this is probably a good place to stop. Thank you very much.
Our conclusion would be that this eta AB is really not a tangent space metric. It's really, it should be interpreted as a second metric with the manifold.
No, this is not something which does this is not a proper metric because it's a gauge field rather than yeah.
And the construction still perturbed the map.
No. So although I didn't, I didn't go through all the details. I have a non-perturbative. The formula I gave give a non-perturbative construction of the theory. So in terms, I mean, I gave explicit forms for M in terms of this interpolating map, and one can choose local frames and work it out very explicitly in terms of the eigenvalues of G and G bar.
So in the case of type 2 supergravity, is there a way to hopefully interpret this from string theory?
That was is essentially Sen's motivation. He constructed a string field theory for type 2b strings, and there was a question about how that could work and how it, particularly how it could deal with the self-dual form, the four form with self-dual field strength. And by looking at what the string field theory did, the string field theory typically introduces all sorts of extra auxiliary fields. And he saw, by looking at the way the string field theory of his kind dealt with that, that inspired him to write down this action. And so rather than deriving it directly from the string field theory, he took a shortcut. But the expectation is that expanding out his string field theory would give this kind of action. So in his case, string field theory, the string field for him, G bar was eta, and in doing his string field theory, it was constructed very much around in flat and 10-dimensional Minkowski space, and
Is there a similar construction for biometric gravities from string theory? Something like that? It seems like the whole problem of the background independence of string theory.
Yeah.
You expand around the background of
Yeah.
string theory. And the string
Yeah.
theory shouldn't have that such.
Yeah. Good. So that's touching on a number of points which I didn't have time to discuss, which is what's the nature of this G bar? In the context of the talk, I was talking about it as a background metric, but one could also have this as dynamical. One could also introduce an action for this G bar, a kinetic term, so this also evolved. Already choosing a background space-time metric places some restrictions, and what one would really like would be to have a proper dynamical formulation where one started off with a Cauchy problem on some hypersurface and chose G and G bar restricted to that hypersurface, and then saw how that evolved. And so one can do that by adding a kinetic term for G bar. And then it's an interesting story that there could be a whole hidden sector of dynamical fields which don't couple to our ordinary fields, and which would be invisible but may be necessary for the consistency of the theory. And and in that kind of context, it's looking a lot like the same sort of story as the multi-gravity sorts of fields. And So locally, so I think what else do I want to say about that? So I think there's it's interesting questions about quite how we think about the second metric, and I think probably one wants to think of it also as dynamical. If one would pose it as a background, that may be too restrictive for some cases. And then there's a lot of formal similarities with the multi-gravity story there, except that one of the gravitons here is invisible.